Hello everyone and welcome to this presentation of our final year project. My name is Arunesh and today I am going to walk you through a framework, a deep learning framework for dyslexia detection via image encoded eye tracking patterns. This project was developed alongside my team members Aravind and Ashish under the guidance of our internal guide Ms. G.R. Kanagavalli. Let's start with the core problem. Dyslexia is a neurodevelopmental disorder that impairs reading fluency, writing, and phonological processing, affecting roughly 10 to 15% of the global population. Unfortunately, current clinical assessments are highly subjective, time consuming, and expensive. This means most children go undiagnosed until they are 8 to 10 years old, missing the window for early intervention. Our research bridges this gap by introducing an objective automated screening pipeline. By utilizing pre-generated eye tracking fixation maps from the benchmark ETDT70 dataset, we perform a systematic comparative analysis using ResNet 18 and ResNet 50 architectures under a strict stratified five-fold cross-validation framework. Our goal is to determine if a lightweight residual model can effectively capture clinical biomarkers without overfitting on limited data sample spaces. Working with eye tracking data introduces severe engineering challenges. Biometric noise, head movements, and webcam data gaps during blinks can easily corrupt the data streams. Furthermore, raw one-dimensional coordinate streams lack spatial context. Traditional machine learning approaches tried to handle this by manually engineering tabular features like saccade lengths and regression frequencies. However, manual feature engineering completely misses the dense spatial distribution across a continuous reading path. On the other hand, complex modern methods like large language models lack spatial intelligence for scan path geometry. Our framework completely eliminates feature engineering by preserving spatial, temporal, and duration data simultaneously within a single optimized image matrix. As you can see in our core system architecture, the pipeline operates across five primary modules: data ingestion, fixed-map preprocessing, dual architecture classification, Optune hyperparameter optimization, and GradCam explainability. We ingest data across three distinct reading tasks from the dataset. Task 1 for single syllables, Task 4 for meaningful connected text, and Task 5 for pseudotext. Task 5 is particularly critical because pseudo words have no semantic meaning. A reader cannot guess the word using context clues. This isolates phonetic decoding deficits, forcing the distinct visual regression patterns that serve as primary dyslexia biomarkers. Now let's step out of the slides and dive directly into the codebase. We begin with Notebook 1, our data ingester and preprocessor. This script connects to our cloud native storage, validates our directory paths, and cross-references our subject matrices with the definitive class labels file. As we scroll down to our visualization cells, you can see how the raw eye gaze data is structured into a fixed-mode token. Fixation duration is explicitly mapped to the area of an ellipse, while chronological time is captured using blue to red color gradient. Look at this side-by-side comparison. The control subjects show clear systematic left to right eye progressions, whereas dyslexic subjects show highly clustered, scattered patterns with severe backwards regressions. We resize these assets to 224 cross 224 pixels and normalize them using ImageNet statistics to ensure perfect compatibility with our deep transfer learning backbones. Moving on to Notebook 2, we establish our baseline model training environment. To protect our evaluation from data leakage, we enforce a strict subject level split, locking away a deterministic 20% validation set consisting of 14 completely unseen subjects. On the remaining 56 subjects, we implement a stratified five-fold cross-validation loop. This guarantees that every fold contains an identical, perfectly balanced distribution of control and dyslexic targets. Another vital technical detail is that no geometric data augmentation is applied to our training images because eye tracking signals rely purely on spatial orientation. Applying random horizontal flips or rotations would reverse reading directions and alter circuit paths, completely destroying the clinical diagnostic signals we need to capture. As we scroll through the logs, you can see our tracking functions, computing accuracy, area under curve, and loss profiles across 50 epochs. To guarantee we are extracting peak performance from our neural architectures, Notebook 3 introduces automated hyperparameter optimization using the Optina framework. We implement a tree-structured Parson estimator sampler across 30 comprehensive trials per task. The objective function adjusts 5 hyperparameters: the learning rate on a log uniform scale, batch sizing, optimizer selection, dropout rates, and weight decay. But accuracy alone isn't enough for a clinical screening tool. If you look at the bottom of this notebook, we implement GradCam, that is gradient weighted class activation mapping. By capturing the gradients passing into the final convolutional layer of our model, we generate visual attention maps overlaid onto the reading paths. This turns our deep network from an opaque black box into an explainable framework, allowing educators to visually verify the exact text zones, causing cognitive drag and regression loops. Notebook 4 acts as our isolated inference testing environment, completely separated from our developmental loops. We load our optimal weights and run predictions against our held out test subjects. Take a look at the terminal output for subject 13. The model passes the subject's fixation images across all three independent reading tasks, correctly identifying them as control subjects and providing precise softmax confidence metrics for every individual classification. Let's synthesize our empirical findings by looking back at our summary metrics. Across our training iterations, the lightweight ResNet 18 architecture consistently outperformed the deeper ResNet 50 model, securing a superior overall accuracy of 88.57%. This milestone successfully outpaces the benchmark metrics established in the Insight 2025 paper by 2.47%. This directly confirms our complexity hypothesis. On a tightly controlled clinical dataset of 70 subjects, massive networks with 25 million parameters suffer from high variance and quickly overfit the training space, leading to extreme validation loss spikes. Meanwhile, ResNet 18's compact parameters act as an organic regulator. Looking at our cross task analysis, task 5, the pseudo text configuration, yielded the most stable and discriminative fixation features across both models, validating its clinical utility. Our final performance plots makes this explicitly clear. If you examine our baseline versus Optina optimized performance chart, you will notice that the accuracy improvement following optimization is minimal. Optina's automated search concluded that our initial baseline configuration, a learning rate of 0.001 combined with the Adam optimizer, was already near optimal. This validates that our baseline pipeline design is exceptionally stable, robust, and highly reliable. In conclusion, our project delivers an objective, scalable, and computationally lean screening alternative that bridges the gap between complex deep learning and interpretable educational diagnostics. Thank you so much for watching, and feel free to leave your questions and thoughts in the comments below.